In this video, we were going to talk about knowledge-based systems. What is a knowledge-based system? We have discussed many things about AI, various application areas, learned some basics, representation techniques, reasoning techniques, and so forth. So we come to a very basic component, which means a knowledge-based system. So what is a knowledge-based system, or KBS I sometimes like to call it? So a knowledge-based system is a computer program that uses artificial intelligence, as simple as that. Okay. One of the basic efforts going on into learning about AI was something called expert systems, right? And expert systems, we'll come to that and discuss a lot more on that. They involve classification, diagnosis, monitoring, designing, scheduling, and specializing, planning for specialized tasks. Okay. And why do we call them expert systems? These are computer programs that use artificial intelligence. So knowledge-based systems are essentially real-world problem solvers. The essential components are a knowledge base. Notice this is different from a database. Okay, there's a knowledge base which essentially consists of facts and sometimes rules as well. Okay. Then it has something called an inference engine. Inference engine. I like this term very much. Inference engine, right? Means something, that is processing something. Yeah, and that's exactly what it does. It is used to infer new information, knowledge from the basic knowledge base that we have. So it applies some kind of a mechanism to infer new information, reason about that, and conclude some solutions. So knowledge base, essentially facts and some rules, an inference engine, which is the mechanism of deriving new information from those facts, and then a user interface. So these are the essential components. We'll discuss further as we go along. So the knowledge-based components of a knowledge base, of course, as I said, it's essentially based on facts. So factual knowledge. This is the information widely accepted by the people who design these knowledge-based systems or expert systems, widely accepted by them, called knowledge engineers. Knowledge engineers are those people who actually create those knowledge-based systems, computerize them, right? So accepted this is factual knowledge, and accepted by knowledge engineers and scholars in this task domain and the domains I mentioned. The other part of this is heuristic knowledge. It's about practice, accuracy of judgment, an individual's ability of evaluation and guessing, right? Heuristic knowledge. I think I've used this word at several other places also, that this heuristic knowledge, in the case of a medical expert, is composed of two components. One is the essential medical knowledge that the doctor has gained by going through a medical school. And then based on that expert actually, when it starts practicing in real life, he begins to learn how to do a quick, accurate judgment, evaluation, and an educated guesswork on the patients that he or she has to diagnose. So over years of practice, this is a basic rule of thumb called heuristic knowledge that is part of the knowledge-based systems. Now we come to the two very basic components. How do we argue? How do we move forward from the information or knowledge that we have? And the first one is called forward chaining. Also known as forward deduction or forward reasoning method, when used in an inference engine. Remember inference engine? It's trying to, Its job is to compile the facts and the rules that are given, and then see how to reason about those facts and maybe come up with new information. So it's a form of reasoning which starts with atomic sentences expressed as facts in the knowledge base and applies the inference rules, modus ponens, in the forward direction to extract more data until a goal is reached. Forward chaining algorithms start from known facts, and it triggers all those rules whose premises, remember premises, if I am sleepy, I will go to bed. This can be expressed both as a predicate in predicate logic form, or it could be expressed in the form of a rule that if I'm sleepy, then I will go to bed. So this statement, if I'm sleepy, let's call it in terms of rules, we call it the left hand side, the premises of that rule. And the right hand side is the conclusion, then I will go to bed. Okay. So forward chaining starts with some known facts, triggers all the rules that are actually looking at those particular facts, and then they execute the action part of the rule, which is the right hand side. So all rules whose premises, left hand side, are satisfied by these facts and add their conclusion to the known facts. Okay, this process repeats until the problem is resolved. Okay, so that's forward chaining, and it is used to create new information or facts. So for instance, as I said, in your knowledge base, you just have one fact, I am sleepy. And here's a rule, as I just mentioned, if I'm sleepy, then I will go to bed. So this is a rule. The inference engine will try and match these two together, okay? And looking for the left-hand side, which is if I'm sleepy, it finds a rule accordingly and then takes the action, which is I go to bed. Now, going to bed is another fact which is inserted. This is like creating new information or facts and added to the knowledge base. This is a strategy used in expert systems to answer the question like, what happens next? What next? Okay. Can we deduce some new information? So, as I said, using this approach, given certain facts, you add new facts, you deduct new facts, infer new facts. And so the inference engine goes through a chain of these conditions and their deductions or derivations, keep on adding new facts until it deduces the final goal. Okay? So what you're doing is you're considering all the facts and rules and then sort them out, okay, one by one before concluding to a solution. So you're kind of moving forward. Okay, you're not looking backwards where this came from. You're saying what will be the effect of this fact based on the rules that we have. Okay. This strategy is followed for working on conclusions or results or effects of some things. For example, prediction of the share market status as an effect on changes in the interest rates. So, for instance, you could say that if the interest rates by the central bank, they are increased, okay, if the interest rates by the central bank are increased, what is the effect on changes on the share market status? You could say increasing the rates will reduce the stock market. Or you could also say that decreasing the interest rates will have a positive effect on the share market. They will go up. Okay. So as you can see here, what we are doing is on the left are a number of facts. Okay. And let's say the first two facts, they combine together, they're and fact 1 and fact 2. You take a decision 1 based on that. And the other two facts, fact 3 and 4, you could say either of them. If fact 3 is true or fact 4 is true, then you take another decision called decision 2. And these two decisions then formulate by ending together. You say decision 1 and decision 2, you arrive at a third decision. So that's how forward chaining works. And as I said, you can relate to real life problems as well. Properties of these forward chaining, other than generating new information, that's kind of a top-down approach that moves from bottom towards the up side. And the process of making a conclusion based on known facts or data by starting from, as I said, from the initial state to reach the goal state or the target state. The forward chaining approach is also known as data-driven approach. Okay, so data derives in the diagram table that we just saw, depending upon the behavior of fact 1, 2, 3, and 4. They are going to derive or affect your decision making. Okay, so this is why instead of us telling them the system what to do, the data tells the system, the forward chaining system, what to do next, what decisions you will come up. Okay, and likewise, this process is repeated, and we reach the goal using the available data. Sometimes the data may not be enough. In case the data is not enough, you don't come up with a suitable decision, right? Like the example I just mentioned, the impact of changes in interest rate. I've just stated a very simple fact, but it could be more complicated, right? It could be linked with, let's say, the general mood of the public, the general economic environment of a country, the weather conditions, okay, and so forth. So what I mean to say is that if the data is incomplete, of course, then your conclusions may not be complete. They could be partially correct. Okay, but that's the way it is. If you have enough information, data, your forward chaining will definitely come up with a solution or goal. All right, moving forwards. Typically, forward chaining is used in expert systems such as CLIPS, in business, as just mentioned, and production rule systems. For instance, I'm reminded of an example of an airline system which actually promotes a set of trained pilots to move from one aircraft to the next. There are certain rules. We say is that pilot A with this much experience, okay, plus X number of trainings, let's say on the new A350 or A380 or whatever, is now eligible for upgrade or moving to the new aircraft. Production system rules actually implemented. They're actually implemented in the system. All right. So what I've discussed so far is moving basic information from basic information, moving forwards towards a conclusion, generating new information. That's forward chaining. As opposed to this, there's something called backward chaining as well, right? Which is right opposite to this. Backward chaining, also called backward deduction or backward reasoning method, when used in an inference engine. So inference engine can work both ways. Okay, it can deduce new information from a given set of information and can go backwards as well. Now, what does going backward mean? A backward algorithm is a form of backward reasoning which starts with a goal and works itself backwards, stepwise, chaining through rules to find evidence or known facts that support the goal. Let me say this again. A backward chaining algorithm is a form of reasoning which starts from a goal and tracks backwards, just like a chain of events, goes through the rules backwards, and to find the facts that actually created this goal. Okay. So instead of moving from here to forward, if I were to do that backwards, how did this goal arrive? How did I come to this? Which facts support this goal? So I look at the rules that have inserted this goal and go and look at their left-hand side, the premises, and who inserted those, look at those rules, then go up to those rules. And from there you go backwards to their left-hand sides, okay, until you come to a point, various words I've used, left-hand side or the premises or the if conditions that lead to these rules, and they are coming to a conclusion. So with this strategy, an expert system finds out the answers to the question like, why did this happen? How did this happen? Okay? And based on what has happened already, the inference engine tries to find out which conditions could have made that happen in the past for this result to happen. So this strategy is followed for finding out the cause, okay, or reason. For example, what caused or what causes blood cancer in humans? Okay, what caused the fire in the building? What caused the blast in a building? What caused that? So you already have a fact called fire in the building, in the factory. Now you want to go and backwards from in your knowledge base and trace backwards using the same rules, going backwards step by step until you come to a point, those facts that could have triggered, let's say, one set of rules, which triggered another set of rules, until the rule that said, it is fire, there is fire. So you want to backtrack each rule that inserted this, the theft or the blast fact. Look at that rule. What conditions caused this rule to fire? All right, you look at those conditions. What rules actually inserted these facts? So you look backwards and you look backwards until you come to those facts. For instance, overheating. So what you do is you're trying to discover evidence which led to this fire. As simple as that. The inference engine will actually trace the rules one by one. They insert the rule that inserted that final fact, look at that rule, and then see how it was triggered, those facts, how were those rules triggered, go backwards. So a chain of events, of rules backtracked until you come to those facts that actually started causing, for instance, mischief or neglect or overheating, okay? Putting in more, let's say, more load than allowed rule or allowed load to be executed. It happens very commonly, okay? So you overload something and ultimately it starts heating up. There should be alarms. Somebody should go and check. Somebody missed out the alarm. So that heating effect caused another rule to fire and another rule to fire until the fire itself happened. So based on what has happened already, the inference engine tries to find out the preconditions, the evidence. So let's look at this diagram here. Once again, you have a decision number 4. And so you want to know how the system arrived at this decision number 4. So there are two decisions which have ended together. So we have just redrawn the diagram that we did before. So decision 4 was caused due to the ending of decision 1 and decision 2. All right. How did you arrive at decision 1? Decision 1 was the ANDing of fact 1 and fact 2, ANDing meaning fact 1 and fact 2 put together resulted in decision 1. And decision 2 is an ORing, okay, either of these, of fact 3 and 4. So fact 3 and 4 ORed meaning either of them is true, that's what led to decision 2. So you can actually backtrack from decision 4 to the facts that led to this decision, and this is what essentially backward chaining is all about. Like a top-down approach based on modus ponens inference rule. And as I said, in the backward chaining, the goal is broken into sub-goals, subsections or sub-goals to prove the facts true. Okay. Now, as opposed to data-driven approach in the forward chaining system, backward chaining system is called a goal-driven approach. List of goals, decide what rules to be selected, and then used for backward chaining, as I just demonstrated. And then we keep on building the chain. Typically, these backward chaining is used in game theory, automated theorem proving tools, inference engines, of course, proof assistance, and various other AI applications. Backward chaining method is mostly used as a depth-first strategy for proving. Okay. So what we learned are two basic things: forward chaining and backward chaining in terms of the rules as well. And these form a very strong basis on which expert systems have been built. I find it very interesting. I hope you did too. Thank you very much. We'll see you next time.